For this example, we're going to calculate the potential as well as the total energy stored. Again, the E stands for electric field associated energy in a coaxial line of length L. So this is a process that will tie together several different concepts in this chapter. So I think it's a good example to go over. And secondarily, the result is something that you would find in textbooks when you're looking at the amount of stored energy in this particular geometry. Now let's recall what a coax looks like. We'll have, first of all, a center conductor, and that's usually where the positive line is, and then outside there is an outer sheath, which is your reference. So this is what you usually set to be ground, and you would put your positive voltage here and your ground here. In this case, we'll set this as being the z-axis, and inside you will also have a dielectric material. In this case, we'll just say the dielectric material is epsilon. This is your reference, and this is your positive voltage. One thing that we'll use is, in this case, you can see there's some symmetry, right? The field will go from the positive to the reference, so the field will spread out radially in each direction, like so, which means that we have symmetry around the z-axis. Or in other words, if we were to do a surface integral along an arbitrary radius that's between the inner conductor and the outer sheath, the field will be in the rho direction, and it will not depend on z, and it will not depend on phi. Therefore, we have the kind of symmetry that we need to use Gauss's law in integral form. Now, the overall journey is kind of a problem type process that I discussed when we were in the module where we were talking about the stored energy. So our plan of attack is that since there's a lot of symmetry here, we should be able to calculate the electric field. So we're going to find the electric field, and then through that, we're going to use that to find V, and we're also going to use that to find the energy stored. But now, after all that talk, let's actually use Gauss's law in integral form to find the electric field. So to find the electric field, we're going to do a surface integral of the toilet paper roll geometry, and it's going to be for an arbitrary radius rho, where rho is between, I guess, a few more parameters to define. The inner radius we'll call A, and the outer radius we'll call B. So we're going to look at, so the electric field would be only in the region between rho equals A all the way out to rho equals B. So we're going to take an integral of this tubular surface as a function of rho going from A to B. Therefore, in order to find the electric field, we're going to integrate along this rho normal surface, so this cylinder here, which means integrating in the z and the phi direction, and that will give us the electric field as a function of rho. And let's set that up. So when doing Gauss's law in integral form, we stop to think. We see that it is symmetric about the cylindrical coordinate system. Therefore, we're going to say we can eyeball it and see that E is going to be in the rho direction. And when we're applying Gauss's law in the cylindrical coordinate system, we see that we're going to use a ds that is equal to, it's going to be normal to the normal direction is going to be rho. So the unit vector is going to be rho, and we're going to be integrating in dz and d phi. And remember, d phi also always has to be multiplied by the radius, rho, and dz is already a unit length. So this is your ds, this is the function, and our electric field is going to be in the rho direction. In this case, one other piece of information, promises the last piece of information I forgot to give you in the beginning, is that you have a surface charge density along this inner conductor, along the surface of this inner conductor of rho s. And the total amount of charge enclosed for a length L will be rho s times the surface area of this conductor cylinder, right? So this is going to be a function of rho because the surface area of this enclosed surface gets larger as rho increases. But note that when you're calculating the total amount of charge enclosed, your function will be held at a constant of this radius a. Because as this green circle expands, the total amount of charge enclosed stays the same, right? It's the total amount of charge that's in this center conductor. So that'll make more sense when we set it up, which is what we're about to do now. So writing Gauss's law in integral form, we have, remember Gauss's law is d ds is going to be equal to the amount of charge enclosed. And remember that d, the electric flux density, is equal to epsilon E. Let's go ahead and just substitute that in. We're going to have the surface integral of epsilon E ds is going to be equal to, let's just start plugging things in. So epsilon, and we're going to say E is E rho in the rho hat direction, dot. We have a rho hat here. We have rho d phi dz. So the rho dot rho gives you 1. This is the thing that you're going to integrate. We're going to integrate in terms of the phi direction. We're going to go from 0 to 2 pi. We're going to go all the way around. For z, we're just going to do unit length. So we'll just keep it symmetric. It's going to be a function of L anyway, so just as long as you integrate it in the length of L, it can be 0 to L or minus L over 2 to L over 2. It shouldn't matter. That's going to be your Gauss's law integral, the integral of this closed surface here. Note that you also have the top and bottom, but we're not going to worry about that because all the field is in the rho direction. So the top and bottom, the unit vectors will be in the z direction, so when you take the dot ds, you're not going to get anything. And so in this case, we're just worried about the rho hat direction. And set that equal to the charge enclosed. Well, what's the charge enclosed again? It's the surface area of this center conductor, which is going to be the circumference of that circle, which is going to be 2 pi a, times the length in the z direction, which is going to be L. And then that's going to be your surface area, so times the surface charge density, rho s. So this is the equation that we're going to solve to get us the electric field. Let's pull out all the terms that don't have anything to do with the integral, which includes the rho term. And remember, this is the key step to make Gauss's law in integral form work, is that you need to be able to pull the electric field components out of the integral. In this case, the electric field cannot depend on phi and z. If it does, then you can't pull it out, which means that you can't just have a bunch of stuff that you can shove over to the right-hand side of the equation. And Gauss's law in integral form will not work as an approach to calculate the electric field. So again, keep that go, no-go criteria in mind when you're approaching these problems. Don't try to force Gauss's law in integral form when it's not going to work. And then you have dz from minus L over 2 to L over 2, and our phi component, d phi from 0 to 2 pi. These are pretty simple integrals. This is going to be equal to L. This is going to be equal to 2 pi. And that's going to be equal to 2 pi a L rho s. Now let's just write this out before we clean it up. 2 pi L epsilon E rho equals 2 pi a L rho s. Conveniently, the 2 pi's cancel out, the L's cancel out, and we are left with our expression for the electric field. So let's just shift up here. Therefore, our electric field, we're just going to divide everything over, is going to be equal to A rho s over epsilon rho in the rho hat direction. Which means that, or actually to keep this notation more consistent, that is our E rho, and if we say that's our E rho, so if we plug that in here, we get that the E field is equal to this in the rho hat direction. And in the D, the electric flux density is going to be epsilon E. So the electric flux density is just going to be the same thing, but without that epsilon term, rho hat. So now with the electric field function, we now have everything we need to calculate the potential energy function and the energy stored. So we're going to follow this, remember this process here. First we're going to find E, which we just did, and that will allow us to find both V as well as the energy stored. So the potential, we're going to go from, remember the formula for the potential is going to be minus integral from the initial position, which in this case is going to be our reference point, so rho equals B, all the way up to some arbitrary position rho. Right, so the potential at any point rho is going to be, if you were to take the integral from your reference point all the way up to rho, because we're looking at the potential relative to the ground. And E dot dl, in this case we have our E. We also see that dl is simply d rho in the rho hat direction, because we're integrating from here to here. We're integrating along the rho direction as we go, as we take this this uphill vector field, this vector field that points in the direction of the uphill, and we integrate it from this point to an arbitrary rho. So plugging in our function here, we're going to have V is going to be equal to minus B to our arbitrary rho value, and this will plug in this electric field, A rho s over epsilon rho, and then rho hat is going to be equal to 1. So then we just have our d rho here, which will allow us to, let's pull out the constants. So minus A rho s over epsilon. And remember the integral of 1 over rho is going to be simply ln of rho. So this is going to be ln of rho minus ln of b. Let's just switch these two because we have that negative sign there. So A rho s over epsilon ln of b minus ln of rho. And then using the fact that natural log of A minus natural log of B is going to be equal to the natural log of A over B, we can then rewrite this as, this is going to be the final answer, so V of rho is going to be equal to A rho s over epsilon natural log of B over rho. And the total energy stored is going to be the same thing, except instead of a line integral, you're going to do a surface integral. So we just calculated this. We're going to find the total energy stored. And the total energy stored, you'll recall, is simply 1/2 the volume integral of epsilon e squared dv. So now let's plug in our E. Again, we like volume integrals because we don't have to worry about calculating anything. It's just always all 3 unit lengths. Right, so you have 3 integrals, epsilon of, while we square it, let's just keep the constants together. A squared rho s squared epsilon squared. And we have 1 over rho squared. And then our unit lengths are d rho And then don't forget, when you're doing d phi, you have rho d phi, so that it's a unit length. You have dz. And now where rho goes from A to B, we're integrating across the entire dielectric region here. Phi goes from 0 to 2 pi, and z goes from minus L over 2 to L over 2. Now you see this, you have this nice little cancellation here, and we're going to pull out the constants and separate out the integrals. You're going to have a squared rho s squared all over 2 epsilon. There's no z, so it's just dz from minus L over 2 to L over 2. This whole thing is going to be equal to L. And then you have your phi. There's no phi, so it's just d phi from 0 to 2 pi. That's going to give you 2 pi. And then you have 1 over rho d rho going from A to B. And with our little exercise that we did here, you can just eyeball this and see that that's going to be the ln of B over A. So then taking all this and cleaning it up, you will come up with the expression of the total energy stored in a cylindrical coax that's charged with a length L, which is going to be equal to pi L A squared rho S squared all over epsilon natural log of B over A. And this is actually a result that you can find in textbooks which you just derived. So since this is a slightly longer journey with a fair amount of algebra, let's just do a quick review of what happened. Our goal was to find the potential and the energy stored. The potential is a function of rho, and it's a scalar function, and the total energy stored within the volume of this cylindrical coax geometry. And we start out by recognizing that this is one of the situations where we're able to find the E field. Specifically, we find the E field using Gauss's law in integral form. We use the geometry, figure out that E is in the rho direction. That allows us to find ds. And as we set it up, we make sure that we recognize that the charge enclosed, if we're only interested in the region from A to B, the charge enclosed stays the same. Right? As this green circle expands out, the total amount of charge stays the same, since it's all the charge that's in the center coax, regardless of what the green line is, as long as you're in this region. The other thing to remember is that for Gauss's law in integral form to work for finding the electric field, you really need the electric field to be something that you can pull out of the integral, which we do here. You pull it out, and then you solve for E. And once you have E, you can then find the potential energy and the energy stored by plugging them into their basic definitions. So the electric field is negative the line integral of E from your reference point to your position of interest. So we integrate it from B to rho, do some algebra, get the result. And then the total energy stored is simply 1/2 epsilon E squared using a volume applied to a volume integral that covers the entire volume in question. So going from A to B in radius, 0 to 2 pi in phi, and then in the z direction for unit length L. And once you sort through that integral, you come up with this expression here, which is something that you can see in textbooks. And that covers a lot of the basic functions that you'll do when the main point still is just be able to interrelate these quantities, the electric field and the potential specifically, but also if you have the electric field, be able to find the energy stored.